All right, so I'm just going to start over. So 5.1, Chapter 5 is all about discrete probabilities. Probability distributions. What they're asking about here is what we have number 4. It says for 100 births, the probability of exactly 56 girls is about 3.9%, and the probability of 56 or more girls is about 13.6%. I'm saying percentages because I think that sounds better in your guys' head. But for solutions, I want these decimals, okay? So when you guys give me answers, give me the decimals, don't give me the percentages. But know how to go back and forth. Okay, so what they're asking is 56 girls and 100 births a significantly high number of girls. Well, let's think about this intuitively. In 100 births, do you guys expect that there could be 56 girls?
Yes.
Yes.
So do you think it's significantly high? I don't think so either. I think that's definitely in the realm of fluctuation. You guys agree? It's going to be a little high, maybe a little low sometimes. So 6 girls above that 50 girls is which we expect 50. You guys agree? Out of 100 births, you expect it to be 50. But there's going to be fluctuation. It's not going to be 50 that often. So it says the probability of 56 girls is 3.9%. The probability of 56 or more is 13.6. So they're saying, is that 56 out of 100 births significantly high? Which probability is more relevant for answering this question? Okay, so let's go back to what a probability distribution actually looks like. Since we're talking about a binomial probability distribution that we're going to cover in the next section, what you're going to kind of notice is that these binomial probability distributions look just like bell-shaped curves. But they're going to be boxes as opposed to smooth curves because we're talking about discrete numbers, right? You can have 0 girls, you can have 1 girl, you can have 2 girls, but you can't have 1.5 girls. You guys agree? Not 1.02 girls and so on. So they're discrete numbers. They are separated. So when we look at it like the picture of a probability distribution or graph, they look a lot like histograms. This is going to be the probability, which is going to be P of x. These numbers are going to range between 0 and 1 because I want your decimal numbers. I don't want the percentages. I want decimals. And then your x-axis is going to be your discrete probabilities. I know the expected number is 50 girls out of 100, right? So sometimes you're going to be a little high, so 51 and 52 and 53 and 54 and 55 and 56 and 57 and 58 and so on. You guys agree? You could also be a little low, 49 and 48 and 47 and 46 and 45 and 44 and whatever. Keep going. You guys agree? All right. What you'll notice with these things is the expected number. You guys agree that the mean in a probability distribution should be the expected number? It should be the highest number here. Since this is bell-shaped, it's going to be the biggest number, okay? If it's like skewed to the right, it's going to be shifted a little to the right. If it's skewed to the left, that means it's going to be shifted a little left. But I know that the highest probability is going to be at this 50%, right? I don't know what it is. They didn't tell me, right? We could actually figure it out in the next section exactly what it is, but right now we don't know. What I do know is that this 56 actually has a probability of about 3.9%. So what I'm going to do is I'm going to say this is about 3.9% here. So I'm going to say this is around 5%, so 0.05. Now I know that basically makes that thing look like 5%, but I'm not exactly sure. We're just going to say that it's maybe somewhere around there. I know that this one is going to be lower. You guys agree? So what you're going to see is this is going to look like a bell-shaped curve. It's going to look very, very nice. These boxes are supposed to be, oh crap, I screwed that all up. Oh well, too late now. So what you're going to see is you're going to see a nice bell-shaped curve here. And same thing in this direction. I'll fix the height of this box. That box is now all messed up. So I'm going to have to fix the other probability as well. I need to be a little more careful next time. So that box is flawed. So instead of that being 5%, this is going to be about 5% here, 0.05. Because what I need this height right here to look like about 3.9%. You guys agree? Okay, so if I track that all the way back, that's going to be 0.0390. All right, so what we know is that the area of this box alone is at 0.0390. You guys agree? That's the height of that box. We want to know if it's going to be significantly high or significantly low. What we know about those things is we use the range of the usual values, right? We know that significantly high, like remember this is going to look like a bell shape. You guys agree? It's going to look something like this. Right? So I know that significantly high and significantly low, I'm just going to randomly guess it. I don't think it's 56. I think it's further, right? it's probably somewhere in the 60s. So I'm going to say somewhere around here, and then also somewhere around here. You guys agree? Now, if what we know is that in between these two hash marks, this is how much of the data? 95% lives in between, right? So 0.95. So how much is going to live in this little tail right here? How much is going to live in this little tail over here? Well, if this is 95%, what are these going to sum to? 5%. Yeah, they're going to sum to 5%. So this is going to be 0.025. I'm going to zoom it out. So this one's going to be 0.025. This is going to be 0.025 because 5% plus 95% is that complete 100%, right? They're supposed to add to 1? Okay. So what I want to know is I want to know if this 56% actually lives inside the tail or outside the tail. Well, if I gather the information, if I take 56 and add probability of 57, so if I take the probability of 56 plus the probability of 57 plus the probability of 58 plus the probability of 59 plus all the way to the probability of 100. You guys agree that would be 56 plus the probability of 57, 58, 59, 60, and so on. You guys agree that this part right here would be the probability of 56 or more? Okay. That's going to be the area of the black, right? You guys agree if the area of the black is bigger than the area of the red, then I'm inside the 95%, aren't I? Okay, so if the area of the black is bigger than the area of the red, I'm bigger than 95%. Well, they said the probability of 56% or more is 1.39, right? Is this bigger than 2.5%? Yes. This is much bigger, isn't it? This is 13%. It's way bigger. It's way inside there, isn't it? Okay. So that's actually how we figure out these cutoffs. Since the probability of the black is bigger than the probability of this little red, it's definitely inside the usual values. So it's not significantly high or significantly low, is it? So when they ask what's more relevant, the height of the box alone or the height of the box and everything to the right of it? Yeah, this is far more relevant. The probability of 56 is always going to be a low number, isn't it? Okay. But the probability of 56 or more is actually a pretty high number. It's above that. It's above that 0.025. Let me pause this. I got somebody asking me a question. She's right, the question. God, why can't everybody just take the fucking hand? Sweet. Okay.
She was 10.
All right, so again, the probability of 56 or more is more relevant than the probability of just 56. So next question we have is number 9. Number 9 is asking for these section. It says determine whether a probability distribution is given. If the probability of distribution is given, I want to find the mean and the standard deviation. If the probability is not given, explain the requirement that has not been satisfied. So number 9, when we want to look for a probability distribution is we're looking for 3 things, right? Step 1, we want to know, is X numerical? So let's take a look. Are those numbers?
Yep.
Yeah.
Good. So step 1, check. Number 2, we have to see if these things add to what?
1.
Do they?
No.
No. Do they? No, they don't. They add to 0.1, don't they? So this is not a probability distribution because the sum of all the probabilities have to be equal to 100%, right? So if we kind of go back to this idea, okay, take a second. So what's the probability that you have 56 girls? Well, it said out of 100 births. So what they know is that it's going to be that, they said it's about 3.9%.
That's right.
So the idea is this probability plus this probability, this probability. If I add up all these probabilities, what should it be? Yeah, because remember, it's really asking what's the probability they have 0 or 1 or 2 or 3 or 4 all the way up to 100, right? You've taken care of every single possibility, haven't you? So if you add up all the possibilities, you add up all the probabilities, it's going to be equal to what? The probabilities of all the possibilities. Yeah, that's a thing. So that's really what you're doing. You're adding up all the probabilities, so it better be equal to 100%. So since this thing does not add up to 100%, it fails to be a probability distribution, which is nice. That means I don't have to find the mean or standard deviation, right? Next question. Okay, number 11. We need to find at least one of them, so hopefully this is a probability distribution. So it says fun ways to flirt. So a sociologist randomly selected single adults for different groups of 3 and ran the variable X as the number in the group who say that the most fun way to flirt is in person. Okay, whatever. Okay, is this a probability distribution? So first, is X numerical?
Yes.
Yes. Like the one above here, you guys agree that number 10 is not a probability distribution because these are not numerical? So that's what I mean by that. They cannot be categorical data. They need to be numerical data for your random variable.
For number 9, it doesn't start with a 0 either.
It doesn't have to.
Oh, it doesn't have
It just has to be numerical. Yep. It tends that most of them do start with 0, but they don't have to. Yep. So X is numerical. Do these things add to 1?
Yes.
Now remember that it has to just add to a number that's very, very close to 1. If you get 1.001, it probably was a rounding error. Remember that we round to 3 sig figs. You guys agree?
Mm-hmm.
So these are all 3 sig figs. So it is possible that you get slightly over 1, and that's okay. So if you get like 1.001, it's a rounding error. It should be equal to 1. So I'm just going to add them up real fast and double check. So I get a 0.091 plus 0.334 plus 0.406. Is it? Good. I'm glad that it didn't add exactly to 1 because I want to make sure that you guys understand that. That right there is pretty dang close to 1, isn't it? So it's probably a rounding error. You know, one of these things had to get rounded up or down, and that's where that is. So yes, the sum of the probabilities is equal to 1, so we're good there. The last thing they ask us to do is verify that each one of these numbers, each one of these probabilities are between 0 and 1. Is 0.091 between 0 and 1?
Yes.
Is that number between 0 and 1?
Yes.
Is that number between 0 and 1?
Yes.
Is that number between 0 and 1?
Yes.
Okay. In my opinion, step 3 is a little irrelevant. We've already said they're probabilities, right? If they're not between 0 and 1, they're not probabilities, therefore it's not a probability distribution. So that's why they want to make sure that these things represent probabilities, and probabilities are numbers between 0 and 1. All right, so since it is a probability distribution, what we have to do is we have to find the mean and the standard deviation. We're just going to do this with our calculator, but I'm going to do the numbers.
Like in number 8, how the x equals 5 is 0 plus.
Yes.
Would you just add 0 in that?
Just treat 0 plus as 0.
As 0.
Yeah. Because the number basically is like 0.000000001. Yep. So yeah, if you see 0 plus, just write it as a 0. Okay, so what I'm going to do is I'm going to find the mean and the standard deviation. We're welcome to do it all on our calculator, but you're going to have to fill out the table. So on your quiz, I'm going to give you guys a table, and I'm going to give you a couple blank columns. And when you guys filling out the columns, is going to be showing your work. Okay?
So it's okay, we didn't make a table on the home.
That's, yeah, no, I'm gonna make a table, and you guys are just gonna fill in the table, so I'm gonna kind of be nice about that. So, for number 11, yes, it's a probability distribution. We've actually figured that out. It satisfies the 3 conditions. So now they ask us to find the mean. So in order to find the mean, what we're gonna do is we're gonna basically take care of this table, and we're gonna extend it a little bit. So I have 0.091, 0.334, 0.408, 0.166. Okay. So what we know is we know that the mean is equal to the summation of x times p of x. Then you're going to sum up all your x times p of x. So the very first column, your next column I should say, the column that you're filling out, so I guess the third column, is going to be x times p of x. Does that make sense? Okay. So you're welcome to multiply these things by hand, but eventually we're going to do this with our calculator. So really, you know, like 0 times 0.9, this is 0, right? And this one's going to be easy too. 1 times this is 0.334. You guys agree?
Yeah.
And then 2 times this is going to be
0.816.
0.816. And then 3 times this?
0.498.
So 0.498. Does that make sense? Another way you guys are welcome to do this, I'm going to show you on the calculator. So you can go statistics. Bless you! Statistics. So we have a edit. I'm just going to clear out 1. Don't delete it. Clear it. So 0, 1, 2, 3. Okay? And I'm going to put all the p of x's in. So the p of x are 0.091, 0.334, 0.408, and then 0.116. So I have that in there, right? Is that clear? So I just filled in the part. So let's take a look at what my thing is labeled and what our calculator labels it. So what's x on our calculator?
L1.
Okay, so this is L1, right? What's p of x in our calculator?
L2.
L2, good. So when I go over to L3, what am I going to multiply together?
X, L2, and L1.
Yeah, x times p of x, but in the calculator it's L1 times L2, right? So in the calculator you're going to go L1 times L2. So the way you do that is you go over to the right, but then you have to go up. You have to press up to be in, like you're highlighting L3. And then once you hit enter, you can actually put an equation in here. So second the number 1 times second the number 2. And what it's going to do is it's going to populate what we just wrote there. Notice the numbers are all the same. You're welcome to do this by hand or you're welcome to use a calculator. I don't care. Either way, you have to know the equation, right? Okay. Now that I know x times p of x, what am I going to do with those numbers? What does this thing say to do with all the x's and p of x's? Okay, so this is going to be equal to 0 plus 0.334 plus 0.816 plus 0.498, right? There's a way you can kind of add all these things up very quickly in your calculator. I'm going to kind of use my one variable stats to do that. So what you can do is you can go statistics, you can go over to calculate, and you can use one variable statistics. And I'm going to put L3 in here, so second 3. And when I calculate this, the only thing that is relevant in this list is the sum of all my variables. So remember that x is equal to our L1, our L3 in this case. So when you do the sum of x, this 1.498 as sum of x, that's the sum of L3. That's what that means, okay? So you can have your calculator do the sum as well. Just remember that all the other numbers are meaningless, okay? You can calculate them, but they don't have any significance.
I got a different sum than
Did you?
Yeah.
What did I do wrong?
I got
Stats.
1.648. That's what I got.
Make sure I got my numbers in here. Oh, why is that wrong?
you did an 8.
Oh, no, I got you. Look, I messed it up. See my 116? That's supposed to be 0.166. So I'm going to have to redo this one. Second 1 times second 2. There you go. Now that'll fix it. So now I go to stats, calculate one variable stats. L3 is good. And I'm just going to take the sum of L3. Sum of L3 is 1.648. 1.648. You're welcome to just add them up. They're only 4 numbers, right? It's not like that's challenging. So back to stats. I'm going to go back to edits, and there's my list again. Okay, so when we do the standard deviation, I'm going to round this later. We're not done. I'm going to actually give a real answer to this because I'm going to round it to 1 decimal past our given variable. But I don't want to do it yet because I still have to calculate the standard deviation. I do not want to introduce any more rounding errors. Is that clear? Okay. So I know that the standard deviation, sigma, is equal to the square root of the summation of x minus mu squared times p of x. So what I'm going to do for this next column is I'm going to do the radicand, which is underneath the radical. Well, this part of it, I'll sum them later. So here I'm going to do x minus mu squared times p of x. Do you see that that's the part before you sum? Because I'm going to have to sum it, then I'm going to have to root it? Okay. You're welcome to do this by hand. I don't want to because it's more complicated now, right? But you can. You remember that, what do we know about mu now?
That is 1.648.
Yeah, so this is now mu. So this is going to be right here, 1.648. So what I get, if you want to calculate this by hand, x in this case is 0 minus 1.648 squared times your p of x, which is 0.091, right? The next one, if you want the hand calculate it, x is equal to 1 minus your mean again, which is 1.648 squared times your p of x, which is 0.334. So you're welcome to do them by hand. What I'd rather do is I'd rather make my calculator do it again. So what's x again? So what's x for your calculator? Okay, so that's going to be L1. Don't forget we got to do the entire equation. Minus what's mu?
1.648.
1.648. And then I have to square it, and then I have to multiply it by p of x. But what's p of x in your calculator? L2. Okay. So that's what I'm going to do. I'm going to go back to my calculator. I'm going to make that happen. So press over to get up to L4, and then press up. Because I have to highlight L4 before I can put an equation in there. So parentheses, again, x is what?
L1.
L1, second number 1, minus the mean, which is 1.648, close parentheses. That was wrong, right? 1.648, close parentheses. Then you have to square it, right?
Yes.
And then I have to multiply by, what's p of x? Second, L2, and then hit enter, and it's going to actually populate all that. Boom is right. So this is going to be equal to, go to like 4 past the decimal. Be honest, 3 past the decimal would be fine. So I'm going to write this as 0.2472. This is 0.1403 if I round it. This one's going to be equal to 0.50506. And this one's going to be 0.3034. You're welcome to use all the numbers, but remember that we're going to round it to 1 decimal past the given data anyway. So if I take it out far enough, I'm not going to introduce any rounding error. What do I have to do with these numbers? I have to add them up. So, yeah, so when you add them up, you're going to get this number right here, aren't you?
Yep.
This is going to be equal to that square root of 0.2472 plus 0.1403 plus 0.0506 plus 0.3034. So this is going to be equal to the square root of, another way you can do it is you can add up all those numbers using one variable stats again, stats, calculate, and then I want to put L4 in here, second number 4. Remember when I calculate, the sum of this, the second line says the sum of L4, so that's what x means. So if you go to stats, calculate, go to one variable stats, and put L4 there instead. When you go down to calculate, that sum of x actually means the sum of L4. Did you guys get 0.741?
Yes.
4-ish? Okay. So 0.741. I'm just going to go to 4. That's pretty good. A quick question. What does 0.7414 actually represent as far as statistics? Yeah, because it's the number before you root, right? This thing right here, this 0.7414, actually is your variance. And when you square your variance, you get your standard deviation. What do you get? 0.4? 0.5. Yeah, we don't even have to go that far out. All right, so remember with rounding. When we round, we have to go one decimal past our given data, right? Well, our given data is our variable. So what's one decimal past an integer? What place? Tenths place. So I'm going to round this 1.648 to 1.6. And I'm going to round this 0.861 to 0.9. And remember, what's the variable? What does x represent? Remember, this is talking about flirting adults. So I'm just going to say adults. Adults. So these are the people that prefer to flirt in person. All right, now that we have all the data, we might as well figure out the usual values. Usual values. I've never missed an opportunity to do that. If I have the mean and standard deviation, I'm always just going to calculate it, okay? So the usual values, take the mean and you subtract 2 standard deviations to your mean and you add 2 standard deviations, right? Technically, you're supposed to use these unrounded numbers, but I don't think it's going to give us much of an error. So I'm just going to use the rounded ones because it's faster to write. And they're not asking for it anyway. So 1.6 minus 2 times 0.9 to 1.6 plus 2 times 0.9.
Yeah.
So I get, what do you got?
Isn't this mostly like could be done in 5 computers?
Oh, sure is. But I might as well do it now. It's the same thing.
Right.
So I know that you can't get negative 0.2 adults, but remember, it's still a statistic. You still have to do it. So let's talk about the discrete numbers that actually live between here. What are the discrete numbers that live between negative 0.2 and 3.4? Remember, these are my possibilities, right? What ones of these numbers live in that range? Does 0 live in there? Does 1 live in there? 2? Actually, all of them, right? They're all usual values, aren't they? 19.
So you look at the X, not P of X.
That's right. Yep. X is your data.
Can you go back to that real quick?
Sure. Go ahead. Oh, this is great. We're gonna number 19 is gonna talk about what we did for number 1. Hey, remember, this is not a video. You know, people look it up too. All right. So number 19. Remember the very first thing when they asked if the number was significantly high or significantly low? This is the exact same idea. Okay, so it's nice to see it twice. So it says for all the numbers between all these problems, we're going to use this chart, which happens to be the number of girls in 8 random births. So it's actually, instead of doing 100, they're doing it out of 8, okay? And they give us all these probabilities, which we'll be able to find in the next section. Those probabilities are not too bad. So try to do it next to each other. All right, so number 19 says, A, what's the probability of what's the probability of 6 girls in 8 births? So what they're asking for is, what's the probability of exactly 6? Exactly 6. Which is the same thing as saying P of 6. Does that make sense? So what we do is we go to our table here, we look at 6, and it's right here. This is equal to 0.109. Does that make sense? All right. B asks us for what's the probability of 6 or more? What's the probability of 6 or more? Yeah, you have to ask yourself, really we have to ask ourselves, is that border included? Is 6 included in the 6 or more? You guys agree that it's included? What if I said above 6? It wouldn't be included, right? 6 or more means probability of 6 plus probability of 7 plus probability of 8, right? But if I say the probability of above 6, I'm just saying 7 and 8. You guys agree? So just make sure that you're reading it. Sometimes they're trying to get clever with their words. So this is the probability of 6 or 7 or 8, right? And how do you find the probabilities of ors? Add them. This is the probability of 6 plus the probability of 7 plus the probability of 8. So we're going to add up the probabilities. So this is 0.109 plus 0.031 plus 0.004. You got a number?
0.144.
Good. What they're asking about is which probability is more relevant to determine if 6 is significantly high? Is it the number from 6 or is it the number from, sorry, is it the number from A or is it the number from B? Yeah, remember what we have here again is if we look at this probability distribution, you're going to have 1 and 2, sorry, you're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, right? These are the possibilities. And if I do their probabilities, 8 is 0.04, so it's very, very small. I'm just grabbing these numbers and going to get a height. So 0.04 might look like something like that. 0.31 is going to look something like this. This is going to be a little bit higher. You guys agree? And then 0.2 somewhere around here. 27% for this one is about here. And then back to here. And then back to here. Back to here. And then back to here. You guys agree that this is extremely symmetric? Do you see your bell shape in there? Okay. So this represents the probabilities. This height right here, which is this top box, is going to be 0.273, 0.273, right? This height right here, which is the height of this box, is going to be the 219, right? This is 0.219. So the height represents the probabilities. So if I want to know if 6 is significantly high, remember what we talk about significantly high and significantly low. If I look at a bell-shaped curve that looks like this, when I'm asking for significantly high and significantly low, I'm asking for 95% of the data, right? So if I look at this picture, I'm looking at this right here, right? I know if these are the usual values, that's 95%. Agreed? That means these tails again are?
0.0.
Yeah, 0.025. They're asking for significantly high, so I only care about this side of it, right? Okay. Since they're only talking about a one tail, sometimes they don't use the 0.025. Sometimes they use the cutoff of 5%. You guys agree we've been using that 5% cutoff a lot? So a lot of times they don't really care about that number. They really just say, don't worry about this side. We're only asking about a right-tailed situation, so they're only asking about that. So if the number is above 5%, if this number right here is above 5%, do you guys agree that this is 5%, right? So let's take a look. I graphed it wrong, but I know that the probability of 6 or more is this, isn't it? It's all those probabilities. You guys agree? And somewhere is a 5%, because actually, you guys see if you look at 7, I have 3% and about that percent. Can you guys see that my tail is, if I want to say 5% for my tail, is going to be this, isn't it? Does that make sense? Because if you look at 7 and 8, 0.031 plus 0.004 is what, 0.035? Yeah, 3.5%. So that right there is 3.5%. So I'd say, like, that's probably going to be my cutoff for significantly high, isn't it? Because this is 0.035, which is 3.5%. And then the entire black, this is what? What's the area of this?
0.144.
Yeah, so 0.144, which is equal to 14.4%. So it doesn't live in this area here. Does it live in this middle area? Yeah, because this is my tail, right? So if it lives inside this middle area, then you know that it's not significantly high. So it's the exact same thing that we did in the very first question, right? Okay. So if this number, essentially, if your sum of your numbers is bigger than 5%, you know that it's a usual value. Okay? So again, if the sum of that number or bigger is bigger than 5%, then it's not significantly high. And if we say the sum of this number or smaller is bigger than 5%, again, it's not significantly high, right? What if this number was smaller than 5%? Yeah, it would live in this tail, right? If it was smaller than 5%, it would just live right here, wouldn't it? Remember, I'm talking about areas. These are areas, right? So if the area is bigger, it's got to be over here. If the area is smaller, it's got to be in here. Which is kind of the same idea. You guys agree? If they've asked before, if it's bigger than 5%, if it's bigger than 5%, it's expected. If it's smaller than 5%, it's not expected. What I'm trying to do is I'm trying to show you the picture of why we say that. 21. I'm not going to do another mean and standard deviation. We did it already. It's on a video. Rule of thumb for significant events.
I guess I'm just kind of confused why you said we use 5% at the end of the tail when on number 1 we use 2.5%. Why did you?
Why did I change it?
Well, I mean, why is it the way it is?
Some situations we say are left-tailed, in some situations we say are right-tailed, in some situations we say are two-tailed. We haven't gotten there yet. So what we're going to do is we're just going to always assume a one-tail situation until I describe that to you. If it's a one-tail situation, that means that tail has to be 5%, right? If it's a two-tailed situation, that would have to be, that's right, exactly. So we're just going to assume a one-tailed situation for right now. And to be honest, it's kind of easier to do it that way. You guys agree? So we just use the 5% to cut it off. We'll get there in chapter 8. Will be when we start assuming more than one tail. Oh, I'm just going to explain. I'm just going to explain 22 to you guys, and then I don't really have time to do it all. So for number 23, I mean, they say use the range rule of thumb for significant events, and what they mean by that is they want to know the usual values. You find your mean, you subtract off 2 standard deviations, you find your mean, and you add 2 standard deviations. You guys agree? So if you use that, you know that you can figure out, these cutoffs, right? So these cutoffs technically, right, this cutoff right here, and this cutoff right here, this really should be your mean minus 2 standard deviations. This should be your mean plus 2 standard deviations. You guys agree? Okay. So there's 2 ways to do it. You can look at the sum of the probabilities to see if it's bigger than 5%, or you can see if the value lives inside this range or if the value lives outside the range. There's 2 different ways to do it. Does that make sense? And what's interesting about the 2 different ways is they both give you the same answer. Is that clear? Because this really represents your 95%. I know that this basically takes in a 2-tailed situation. You guys agree? And I say we're mostly going to do 1-tails. But the way they set it up is it's just still going to work, okay? That the sum of the probability is going to be usually above 5% anyway, okay? So you're going to see if it's a usual value. So one way you guys can do this is for 23, you can find the mean and you can find the standard deviation just like we did before. And then you can see if 3 adults live inside that plus or minus 2 standard deviations. Another way you can do this is you can take the probability of 3 plus the probability of 4 plus the probability of 5, add those things up and see if it's bigger than 5%. And it is, isn't it? So what you'll notice is that, yes, it's a usual value either way you slice it.